Fourier analysis on Z mod n, right? So the cyclic groups, finite cyclic groups. So what is it? So remember that what we are looking for are characters of a group. Okay, so let's stick to particularly Z mod n. Character means homomorphisms from the group into the circle group. Okay, so when the group has some obvious metric or topology, then we ask in addition that this homomorphism should be continuous. But otherwise, for finite groups, such a condition is redundant. So we are considering discrete topology. So it's just all homomorphisms. And for Z mod n, it is easy to figure out that all the homomorphisms are basically uh, these. One second. So yeah, so these chi sub k, or what is it? Chi sub k of j is e to the 2 pi I j k by n. Another way to write it is, if yeah, so sending j, if here I am writing zn as 0, 1, 2 up to n minus 1 with addition modulo n, then j goes to e to the 2 pi I j k over n, where k is fixed. You can fix any k also between 0 to n minus 1. Then each of those k will give a homomorphism from zn into the circle group. Okay. Actually, if you write, so I didn't say it, but if you write Z mod n as in the multiplicative way, so instead of taking 0, 1 to n minus 1, you can take the nth roots of unity. Then this homomorphism is just z going to z to the power k. Okay, so those are all the homomorphisms. Anyway, so and we defined the Fourier transform, which is if you have a function on the group, that is in this case Zn, then its Fourier transform is given by okay, so sorry, before that these characters, they are functions on the group and they form an orthonormal basis. After dividing by square root of n, they form an orthonormal basis for the set of all functions on Zn. Okay, and so therefore you can expand any function in terms of that. The coefficients, though those are called the Fourier coefficients of f. Okay, so from f you get another f hat. If f is a function on 0 up to n minus 1, f hat, for each character there is a coefficient, so that we write as f hat of k. Since I am identifying the character, this character with k, we write it as f hat of k. So that is the Fourier transform, and we saw a couple of things about it. So it looks very similar. So that is what Fourier inversion is, and because of this being an orthonormal basis, there is a Plancherel theorem. The L2 norm squared of f will be the same as sum of squares of the Fourier coefficients. Okay, so this is what we saw, and I saw a couple of examples. Okay, so that's a quick recap. And then I said, question is whether we can go more general and ask for other groups. If I take some general finite group and look at the characters, will I get an orthonormal basis? Okay, so let's first address that question. So I will always write n for the size of the group. Okay, I mean, unless I have some, if I'm studying specifically Z mod n or so on, then I may have a small n, but in general, I'll write n, capital N, for the size of the group. So will characters give an orthonormal basis? That's a question. Okay. Now, what I left, I mean, I left this as exercise. Did anyone try this? So I said that for even the smallest one, the non-abelian group here, symmetric group on 3 elements, you don't have, if you have to get a basis, you have to have n characters, capital N many characters. But for S3, which has order 6, there are 6 elements in S3, but there are only 2 characters. Did anyone solve this problem? So did anyone figure out that you don't have enough characters here? Well, the one can do the specific case. Let me leave that and then let me give a general reason. So the point is, see, notice. So suppose chi is a character. then chi of, if you take x, y, x inverse, it is chi of x inverse, which is also chi of x inverse. But this is an abelian. This is abelian. Therefore, this will cancel, and you just get chi of y. Right? Because the target group is abelian. What this shows is that I is constant on conjugacy classes. If two elements are conjugate to each other, like x, y, x inverse and x, sorry, what did I do? And y, sorry. Y and x, y, x inverse are conjugate to each other, and the character value must be the same at those 2 points. That means, so this entire group, on each conjugacy class is the equivalence class of this, right? So chi must be constant on each conjugacy class. So any two things which are conjugate, the value will be the same. Hence, to get n characters, we need how many? I mean, so well. So what will be the dimension of the? So it's constant on each conjugacy class, right? So how will you get n-dimensional space actually? So the only way they will form a basis. So two things that are conjugate to each other cannot be separated by characters. Hence, for characters to form a basis, all conjugacy classes have to be singletons.
Sir,
Huh.
why is chi of
Yes.
x inverse the same as chi of x whole inverse?
That is part of homomorphism, right? So chi of x inverse should be chi of 0, which is 1. I mean, on the torus side, the identity is written 1, but it is chi of x into chi of x inverse. So this
Okay.
is the inverse of this. Yeah.
Thank you.
So group homomorphism just means the group property is preserved. So yeah. So inverse will map to inverse. Therefore, and this is abelian. That's what I use. Therefore, this can cancel this. If it was not abelian, of course, we can't say anything. But it's abelian. Therefore, I cancel this with this and got chi of 1. So if you have to, so in L2 of GC, if you take any x and any two elements like this one, if you call this z, z and y are two distinct elements. If z and y are two distinct elements, there is always a function which has a different value at z and y. So such a function cannot be written in terms of as a linear combination of characters, since characters give the same value at both points. Therefore, for characters to give a basis, all conjugacy classes must be singletons, which is same as G is abelian. Okay. So, I mean, I'm not saying that if G is abelian, you have it. If characters form a basis, it is necessary that all conjugacy classes must be singletons. And conjugacy classes are singletons means what? I mean, anything conjugate to y is of the form x, y, x inverse for some group element x. That has to be equal to y means y, x, y, x inverse equal to y, or x, y equals yx. So y commutes with everything else. So that happens for every y. So G is a abelian. So if any group is, I mean, I have shown a strong thing here. You take any non-abelian group, you don't have enough characters. Okay, you can't have a full basis of characters. That is clear. I hope is that okay. So that also answers the case of S3, but even you may not have, what you may expect is, okay, can I have number of characters equal to the, what is the dimension of the span? So what another way to say it is here, so as a corollary here, what we get is that the span of all the characters is the dimension is less than equal to number of conjugacy classes. Since they are constant on conjugacy classes, the dimension can't be more than the number of conjugacy classes. But even that number is not achievable. Okay, so in S3, for example, in S3, I mean, or you take Sn, for example, Sn, n greater than equal to 3. So this has only 2 characters. So this is an exercise. I will leave it for you to think. So basically, why? I mean, so in particular, S3 has 3 conjugacy classes. S3 has what all? It has the identity 1, 2, 3. Okay, so the let's write in cycle notation. So there is the identity. There are the 3 transpositions. Then there is the 3 cycle. I mean 2, 3 cycles. Okay. So the conjugacy classes are. This is one conjugacy class in itself. Always. The 3 transpositions form a conjugacy class, and the 3 cycles form a conjugacy class. In general, the cycle structure gives you the conjugacy classes. Okay, it's not just in, if you go to S4, there are different possibilities. I mean, so an element of Sn will be a product of cycles. Now, the sizes of those cycles will give you, specify the conjugacy class. Anyway, here there are 3 conjugacy classes, but only 2 characters. What are the 2 characters, by the way? In S3, what are, or S10, what are the 2 characters?
All going to 1 or all going to -1 probably?
No, this other one is the sign
Oh, no.
character.
No,
That means
so
order.
and everything to minus. Huh? Yeah.
Other one is the sign character. I mean, odd
Right.
permutation.
Oh, yeah. Okay.
One and the trivial character and the sign. The trivial character and the sign character, these are the 2 characters. Okay. So, and there are no other characters. Okay. Okay, here I'm using the word. So first, those of you who have learned more, I mean, there is a more general definition of characters when you go to non-abelian. There is a good representation theory of non-abelian groups, which we are not going into. So there, what one looks at is not homomorphisms into the torus, into the circle group. So the more general thing is to think of circle group is the same as 1/1 unitary matrices. Okay, 1/1 unitary matrices means you have a single number matrix, 1/1 matrix with one entry which has absolute value 1. So it's the circle group is this. So when one studies more general groups, one looks at homomorphisms into general unitary groups, and so the and define characters in terms of that. If you do all that, then you get the number of the span of the characters. In the more general definition of characters, the dimension will become equal to the number of conjugacy classes. So, but we are not interested in the non-abelian case, so we won't have anything to do with that. There is a Fourier analysis for non-abelian situation also, but we are not going there. Okay, and so this is where we will stay. So at least the non-abelian case is, it seems, is not possible. Okay, and okay, so what can we do? Okay, any questions? Okay, so let's go to the general. What about abelian? Okay, can we do it for abelian groups? Rather than do that, let's go in the positive direction. So we know that we have a Fourier. So suppose, so what groups can we? For what groups can we get a full basis of characters? Okay, I'm at the moment looking only at finite. Okay, so now a necessary condition is it should be abelian. Okay, so let's see. What we know is that Zn is good, right? Cyclic groups are good. Now let's see if we have it for some groups, can we build more groups for which it is good? So here is an observation. So take two groups, G1, G2, two finite groups. Actually, I mean, I don't even have to say finite. Okay, we are anyway working with finite groups, but this part is also sometimes some things may be more general. So two finite groups, and let's say here I have a character chi1 and here is a character chi2. So that means they are homomorphisms into the circle group. Now I can form the product group G1 cross G2. So this is just all pairs, right? So direct product of and element wise operation here. That's what it is. X1, Y1. If you write in multiplicative notation, X1, Y1 into X2, Y2 will be coordinate wise multiplication. So that's a group actually. So this is a group. And if G1, G2 are finite groups, this will be another finite group. What I want is, can I use these characters to build a character here? So let's let chi be chi1 tensor chi2. Okay, so what is tensor? Tensor means introducing variables. So it is a function like this, chi of x comma y is, it's a tensor of these two. So chi1 will act on the first variable and chi2 will act on the second variable. That's what tensor means. Tensor means there are different variables. It's not, don't call it product, it is tensor product. So tensor product of these two functions. In general, you can define tensor product of two functions. Okay, so this part has nothing to do with the group structure. If you have two Cartesian product of two spaces, then that if you have a function on the first space, a function on the second space, then you can make a function of two variables by taking this kind of product, f of x times g of y. That's called a tensor product. So this is, you define like this. So then the point is, in this situation, chi is a character of G. Why is that? I mean, the homomorphism property is all you need to check. You look at what is chi of this. Okay, hardly need to write, but that is by definition chi1 of x1, x2 and chi2 of y1, y2 by definition. And since these are characters, this splits as a product. And this is chi1, chi2 of y1, chi2 of y2. And now these two, chi1 of x1, chi2 of y1 will give me chi of x1, y1. That is because of these two. And so on, chi of x2, y2. Okay, so it's just a trivial, straightforward check. So if I have two characters of these two groups, I get a character of the product group. So what this, so this is one way to make a new group with a lot of characters. Why? I mean, if originally, so I hope this is clear, right? I mean, so direct product. So this is the direct product of two groups. Then characters of the individual groups. If I have some characters here, I'll get a character of the product group. Because of that, if G1 has N1 characters, so N1 is the size of G1. Suppose it has a full basis of characters and G2 has N2 characters where N2 is the size of G2. Suppose G1 and G2 are good groups in my sense, that is they have a full basis of characters. Then G equal to G1 cross G2 has N1 into N2 characters. Why? I can take anything here and anything here and take a tensor product. One has to be slightly careful. Are they distinct? Just because you write different notation doesn't mean they are distinct, but it's a point to check, are they distinct? But they are distinct. For a moment, let me assume that. It's an easy check. But N1, N2, so you get N1, N2 characters, and N1, N2 is the size of G. Implies G has a full basis of characters. Okay. Oops. So if you have two groups which have full basis of characters, then the product group also has a full basis of characters. That is the point. Everything staying with finite. In the infinite situation, I cannot argue like this. Then the dimensions will be infinity. Here it matters that ni's are finite. Okay. So it's only for finite groups that I am arguing this. That if I have two groups which have full basis of characters, then the product group also has a full basis of characters. So as a consequence, what do we get? I mean, we already have the only groups I know is Zn. So I can take products of those. So that is hence any group of the form. So I can keep taking products. Okay. So I can keep taking products. If I take Zn1, Zn2, and any finite number of things Nk, any Ni. So there is no need to take Ni equal to 1. That's a trivial group. Ni greater than equal to 2 is good. That is has a full basis of characters. Any product of cyclic groups is good. So this is the positive side. On the negative side, we saw no non-abelian group is good in our sense, but every product of cyclic groups is good. Now, what are all products of what are all the groups I can get like this as products of cyclic groups?
Any abelian group.
Any abelian group. That's the structure theorem, right? So there is a theorem, structure theorem for finite abelian groups. All abelian groups sorry, I should say finite. All finite abelian groups are of this form. In fact, there is a stronger, I mean, sort of statement in how the product happens. You can take so G is finite abelian. So I'm stating that in a slightly finite abelian group. And let's say n is the size of the group is, let's say you have a prime factorization p1 to the okay, yeah. So you can write actually. So the what I want to say is let me not write prime factorization. N is the size of G. Then G is isomorphic to some Z n1, but this n1, each ni can be taken to be prime powers. Let's write P1 to the M1 cos. So it can be written like this, where each Pi is prime. Mi greater than equal to 1. So obviously n has to be the size of G will be the product of this. The reason I didn't want to write it as prime factorization is that this is not necessarily the case. So P1 may be equal to P2, not necessarily distinct. So this is a slightly stronger statement, but I don't really need this. All I want to say, all I need is that you just take this for granted. If you do not know this fact, you just take it for granted. Actually, we will not even be using it. In any example, you can, if you have any examples, so actually this course will largely work on examples. I mean, we are not interested too much in the generalities. I mean, we'll be working with specific groups and so on. So in specific situations, you can always check this, that your finite abelian group is of this form. Okay, so if you are not familiar with this theorem, then you can just take this for granted. That's all. That any finite abelian group can be written as a product of cyclic groups. That gives us the pleasing point that any non-abelian group did not work and every abelian group is good. Okay, so that is the corollary that I will take. So then it has n characters. Okay. Actually, how do I mean? So that point I kind of skipped over. How do I know that they are distinct? That is important, right? I mean, so that here when I take the product of two groups, I had n1 characters here, n2 characters here, and I took the tensor product. Are they distinct or are they not distinct? It's actually just there are many ways to see that they are actually distinct. For example, you can take the first coordinate to be identity. I mean, you have two products. I mean, whether chi1 tensor chi2 can be equal to chi1 dash tensor chi2 dash. That's the question. You just figure out that by just specializing to the elements where one of them is identity, you can just recover chi1 and chi2 from chi, right? See, from chi, you can get chi1 by just evaluating at x comma identity, and you can recover x chi2 by evaluating at identity comma y. Therefore, you can recover the two characters from the product character. Therefore, they have to be distinct. So that's why you get n1 and n2, and that is why you get a full basis. So n is the size of the group. So full basis of characters. Okay, so we get n characters. Okay, whether they form a full basis is a question. Okay, at least we get n characters. Let us say. We don't know whether they may be linearly dependent. For all we know, right? Actually, yeah. So I have not actually said they have full basis. All I have said is they at least have the required number of characters. Is it okay? So let me pause here and take questions. If I kind of skip some things or any questions here. So what I have argued is that in finite abelian group, the number of characters is equal to the cardinality of the group. Now I want to say that they are actually linearly independent. Are there any questions? Okay, so how do I show they are linearly independent? So I'm in this setting. The characters are in fact so one way is you can go back here and check if any such products are they going to be linearly independent. You can do a laborious, somewhat tedious calculation and probably check from here that these n1, n2 characters are not merely distinct, but they are linearly independent. Okay. I mean, in fact, actually, if you have done this, you may have done this in groups. I mean, if you have a product of two vector spaces and you have a basis for both, then for the tensor product, then you can get a basis consisting of the pairwise tensors of these basis vectors. If you have done that exercise, then you have done this because these n1 characters form a basis for L2 of G1. These n2 characters form a basis for L2 of G2. And you are taking all the pairwise tensors, so they should form a basis for L2 of L2 of G1 tensor L2 of G2, which is actually L2 of G. That identification you have to make. But here is another way, which is actually somewhat historically, this may be with a more, I mean, this is maybe closer to history. So the way to check that they are linearly independent. So when we teach linear algebra, so concepts get recast in different ways. So we talk about linear independence, vector spaces, and so on. And much later we talk about inner product spaces, orthogonality. But the way things were born, one of the key observations of Fourier was the orthogonality, and linear independence came from that. You can't have linear independence because they are orthogonal. So what we will argue is that in fact they are orthogonal. Okay, so because they are orthogonal, they can't be linearly independent. Okay, unless one of them is zero, but none of them is zero. You will see in a moment. So let chi1, chi2 be characters of G. So take two characters of G. So let's look at, or rather, let's take a single character. First, let me make a small observation. Let chi be a character. So if you look at, if you add it over all the elements of the group, what do I get? Okay. So what I want to say is that here I will get 0 most of the time. Of course, if you take the trivial character, chi of x is 1 for every x. So if it is n, if chi is the trivial character. Okay, trivial character means everything is mapped to 1. That's the trivial homomorphism. But anything non-trivial homomorphism, the sum will give me 0. This is exactly like we had in the case of Zn, right? I mean, so the sum of roots of unity give. By the way, all this you can derive from there because you have the structure theorem. You can write down the characters explicitly. So this is not a different fact. You get it from the same fact. But it's actually more interesting to do it like this. Here, I'm not actually using that it is in the structure form. I mean, I'm not using the sums of roots of unity directly speaking. I mean that these things come from roots of unity and powers and so on. I'm not using that directly. Just the fact that they are homomorphism, I will say that this shows that this sum has to be 0 or n. N if it is trivial, 0 otherwise. So the reason is nice. You take this thing, okay? So if you multiply by, so if, so fix any x naught in the group, okay? So suppose I take chi of x naught times, so let's take this number which I am interested in and multiply by chi of x naught. What do I get? So when I multiply chi of x naught into chi of x, I get chi of x naught x. Okay, I'm just writing multiplicative notation. This actually works in non-abelian setting also, but if you want to write plus, I don't care. So I will kind of sometimes move between plus notation and product notation. I don't think it will be any confusion. So, but what is this? I have fixed an x naught and I'm summing over all x of x naught x, but that's same as summing over all the group elements, right? So if I call this y, then it's just when you multiply by x naught, it just gives a bijection of the group into itself. So what this shows is that either chi of x naught equal to 1 or the sum must be 0. Okay, so either this character value here must be 1 or this thing must be 0, but this is true for all x naught. Hence, either chi is trivial or else the sum is 0. That's what I have written here. And when it is trivial, it is a direct check. It's all 1, therefore the sum is n. Okay, so we get this, but from here the orthogonality is immediate because if chi1 and chi2 are two characters, then what is the inner product in L2 of G? By definition, that is just sum over x in G of chi1x, chi2x conjugate, which is, you can take this as, chi1, chi2 bar of x. Okay, so this is a character. Chi2 bar a character actually. It is chi1, chi2 inverse if you want, because on unit circle conjugating and taking inverse is same thing. So it is chi1, chi2 inverse of x. So this is also a character. So this is actually 0. This is n if chi1 of chi1, chi2 bar is trivial and 0 otherwise. But this is same as chi1x, chi2 bar x is 1, right? Chi1x equal to chi2x for all x in G. That is chi1 equal to chi2. So what we see is that the inner product is n if chi1 equal to chi2 and 0 otherwise. So that therefore you get again that 1 by square root n chi. Now let me introduce a notation. G hat. Okay, so G hat is the set of all characters. So let's give that name here. So G hat is the set of all characters. Then this forms an orthonormal basis. Okay. Any questions here? So I have shown that in fact they form characters are not just linearly independent, they are orthogonal in L2 of G. So they are of course distinct and they have norms which are n. So I scale by square root n. I get an orthonormal basis for L2 of G because why orthonormal basis? They are orthogonal, but the size is the same. Okay, because so here we are using so what this shows, this reasoning shows that they are orthogonal, but because the size is because the size of G hat is the size of G, which is the dimension of L2 of G. Therefore, I have a full set, so it is actually a basis. Okay, so that completes the proof. So it's So any finite abelian group, the characters form a orthonormal. Well, let me be loose and say they form an orthonormal basis. You have to scale by square root 10 to get an orthonormal basis. Okay. I find it somewhat thrilling. I mean, maybe I don't know, but here the thing is, character is a kind of purely group theoretic notion, right? We are in a finite abelian group, and we are asking for a group property, homomorphisms into the circle group, and that gives you this sort of, which I think of as analytic or geometric property of orthogonality. I mean, it's quite amazing. I find it somewhat thrilling. Yeah. Anyway, so any questions, comments here? Okay, if not, let me proceed. So for a group, we have so I didn't give any examples at the moment. Okay, maybe I do a couple of things and then give examples. Okay, so a very important example that hopefully we will use a few times. We'll come to a few times. Okay, so now having the full basis, so now onwards, I'll be working with G, finite abelian group. N is the size of the group, and G hat is the set of characters. And what we saw is that chi over root 10 chi in G hat is orthonormal basis for L2 of G. So you can definitely expand any. So if I have any function, I can expand in this orthonormal basis. So f is a function from G into complex numbers. So I always take L2 of G for me will always be complex valued functions, by the way. I always take complex valued functions. So suppose f is in L2 of G, then we can write f as sum over chi in G hat, f inner product chi over square root n times right. So this we can write because that's the way you expand. Actually, I'm now slightly right. No, it's correct. It's correct. So this, which we will call. So let's call this as f hat of
Sir,
chi.
you don't need that 1 over root n, right? That is included in.
Where
Do we, because
this is the orthonormal basis. I have to take f inner product with an element of the orthonormal basis, and then the orthonormal basis element, right?
yeah, G hat doesn't include the 1 by root n, only chi's.
No, G hat is characters. Chi. G hat consists of chi characters. They are mapped into the circle. It is, but they don't form orthonormal basis. They are orthogonal. So I divide by square root 10, then they form orthonormal basis, right?
Yeah.
Maybe am I understanding? I mean, so chi over square root 10 is the orthonormal basis. So this formula, when I have an v1, v2, vn is a basis in some vector space, then to write fvi, vi, this is the expansion if that is an orthonormal basis, not in general. So that's why I take f inner product this times this. So did I answer your question or maybe not?
Yes, sir. My doubt was if the definition of G hat included the factor 1 over root n. It didn't. Yeah.
No, G hat doesn't I mean, G hat are not scaled characters. G hat for me will be unscaled characters. They are just homomorphisms. Yeah, if you scale them, they won't be homomorphisms. It's okay. So you cannot scale homomorphisms. In fact, it's a point that I did not say earlier. but why the target is circle group? If you make the target to be characters also, they have to map into the circle group. Anyway, whatever it is, so G hat consists of characters which are homomorphisms into the circle group. So chi values will be 1, absolute value will be 1. But they will not form orthonormal basis. To get orthonormal basis, I have to scale by square root 10. So here, but the indexing set I can use as G hat, right? I mean, that's not a problem. So here, I don't have to write chi over square root 10. I mean, I write chi in G hat. Yeah. So this will be f hat of chi. This is the definition of f hat of chi times chi 1 by square root of n. Okay, where f hat of chi is 1 by square root n f inner product with chi. Okay, so just to write it out very explicitly, what this means is, of course, this means 1 by square root n sorry, my chi and x are very similar. Maybe I should have, yeah, I should use this other x, small x. So this is the inner product, and this one means point by point. Okay, so what this means is, of course, that any f of x, well, this is a finite dimensional vector space, so L2 expansion, pointwise expansion are all the same. Chi in G hat, f hat of chi is a number, complex number times chi of x. So you're writing f of x as a superposition of characters. Any function can be written as a linear combination of characters. The coefficients are this f hat. So f hat is a function. So f is from G to complex numbers, gives f hat, which is a function from G hat into complex numbers. Okay, and this is called a Fourier transform. So this thing, this mapping f to f hat is called a Fourier transform, or if you want, it's a Fourier transform on the group G. So this is the Fourier transform. So we say f hat is the Fourier transform of f. Okay, f hat is called the Fourier transform of f, but Fourier transform itself is the mapping that takes function on group to function on the G hat, function on G to function on G hat, like this. Is okay. So that is what we call Fourier transform. So one immediate, so something is a little bit not consistent with Zn. That I will come to. In fact, it is a, that's why there is a slight, going to be a slight issue, important point I'll come to later. But one thing that we immediately get is the Plancherel relation, like before. The Fourier transform L2 of G to L2 of G hat, because any functions on the finite sets we can call L2 of that set. Okay, L2 means always counting measure on the group. I mean, so on the, not necessarily group. I mean, G hat here at the moment has no states, just a set. Is unitary. What that means is, if I take inner product of two things in L2 of G, then it is the same as the inner product of f hat and G hat in L2 of G hat. In particular, if I take this norm square of a function on the group, it is sorry. It is the same as the f hat norm square on G hat. Okay, as I said, this is just a finite set at the moment. G hat is not a group as far as we can see. So what this means is summation f of x square is summation f hat of chi. That's what this is, and similarly you can write that one. So that's the Plancherel relation. It's immediate from this orthonormal expansion, right? Anytime you expand, that's what you get. Okay, so that we have, but what is different from Zn, if you notice one point in Zn, I was not writing f hat of a character, I was writing f hat of k. In Zn, one point was the Zn was 0, 1 up to n minus 1, right? And the characters were this chi k, e to the 2 pi I j k. Somehow there was naturally, the characters could be also identified as 0, 1 up to n minus 1. Right, because chi k, I just called it k. I wrote f hat of k. I did not write f of k. I mean, what did I write? Here, f hat of k is what I wrote instead of writing f hat of chi k. From our new notation point of view, that's an abuse of notation, but this one had a somewhat of a coincidence that g hat naturally was also indexed by same as 1, 0, 1 up to n minus 1. That is not clear in the general situation. That whether G hat is in bijection with G and G hat have the same number of elements, but can I identify, is there a natural bijection between G and G hat? In general, actually no. So we'll leave it at that. Okay, so we'll leave it like that. We'll write f hat of a character, but when we do Z mod n, then we will write abuse notation and write f hat of k. Okay, so what structure G hat and so on, I will come to next time. Are there any questions so far? So what I have done is I have defined, so summary of what we have done so far. For a finite abelian group, we have a full set of characters which form an orthonormal basis after scaling by root n for L2 of G. Therefore, functions on the group can be expanded in the characters, scaled characters, and the coefficients essentially are what we call Fourier coefficients, and this naturally gives the Plancherel relation. Okay, that much we have done. Now there are two other things we did last time. For example, Fourier inversion. Fourier inversion makes no sense quite here. Well, it's a unitary transformation, so you can, that means it's invertible. From f hat we can recover f, but we can't take Fourier transform of f hat. It doesn't make sense unless G hat is itself a group. Does G hat have a group structure, etc.? That is something I will investigate next time, but we'll leave that for next time. What I want to do now is an example. But if there are any questions, let me take that first. Are there any questions? Okay, if not, let me do one example of considerable importance. G is Z2 product with itself n times. Okay, Z2 to the n. So if you want, it is all x1, xn, xi is plus 1 or, okay, so it's a question of how you want to write the notation. There are, of course, you can use 0 and 1. Let me use minus 1 and 1. I mean, one will, it's just easy to flip between this. Where minus 1, 1 is a, so this is with multiplication, of course. So when I write Z2, I often use the additive notation 0, 1 with addition modulo. But say they are the same thing. Here, let me use multiplicative notation. So then, what are the characters of Z2? So Z2 has only two characters, right? One is chi 0, which is the trivial character. So this is the trivial character. And I have another character which is chi1 of 1. What is the other character? You have to map this to a circle group. So you can send -1 to -1 and 1 to 1. So this is the non-trivial character. If you are talking in terms of Z2, you will send 0 to -1 and 1 to 0 to 1 and 1 to -1. Well, okay, here it is 1. Identity is 1. 1 goes to 1 and -1 goes to -1. These are the two characters. So what are the characters of Z2 to the n? Okay, so they will be of the form I can take. I'll have to take tensor product of these characters. So each time I have two choices, right? I have choice of chi. So let me write chi epsilon 1 tensor chi epsilon 2 tensor chi epsilon n, where each epsilon I is 0 or 1. So I have to take one character for each of these product parts, and I can take either the trivial character or the non-trivial character. Okay. So, but what does that do? I mean, so what is chi of x1, x2, xn then for this? So what matters is, so let S be the set of all I such that epsilon I is 1. That is the coordinates for which we take the non-trivial character. So what do we get here? So this is chi epsilon 1 of x1, chi epsilon 2 of x2. By definition, tensor product just means that up to chi epsilon n of xn. So any. It's 1 o'clock. Okay, I will just stop in a moment, in a minute. So all those epsilon I which is not in S anyway, it is going to be 1. So this is going to be only the I in S matter, because everywhere else it is anyway 1. So I don't even need to write them. The trivial characters are 1. So it's the non-trivial characters. Well, this could have been written as chi1 of x is x, right? I mean, -1 goes to -1, 1 goes to -1. So I can write it as product of xi. Okay, chi of x1, x2, xn is the product of xi, I and s. So we will denote this by chi s. So the characters of Z2 to the n, in other words, are chi s, where S is a subset of n. When I write square bracket n, I mean the set 1 to up to n. So we can index the characters by subsets. And chi s of x is just this. This is the chi s of x. You just take the product of xi's, I and s. Don't use this notation when you take 0, 1. It is when you take -1, 1. So these are the characters of the Z2 to the n. Okay, I will stop here. We'll continue next time. But if people have questions, welcome to stay and ask.